energy, the cost for energy are actually our problems.
So that way this topic very interesting, correct? Very interesting.
Good morning, everyone, and a warm welcome to the inauguration of the GIAN course on Combustion Theory and Application. It's an honor to host this prestigious program, which aims to foster global collaboration and knowledge sharing. We are honored to have among us today Chief Guest Professor Sukumar Nandi, Dean of Administration, IIT Guwahati, Foreign Expert Professor Detlev Markus, Head of Department, PTB, Braunschweig, Germany. Professor Samantha Hajarika, Head of Department of Mechanical Engineering, IIT Guwahati. Professor T. Venkatesh Bharat, Local Coordinator of GIAN and Head Center for Education and Technology, IIT Guwahati. Professor Niranjan Sahoo, Course Coordinator of the GIAN course and Faculty in the Department of Mechanical Engineering, IIT Guwahati. I request all the dignitaries to please come on the dais and have their seats. Please, sir. Professor T. Venkatesh Bharat, Local Coordinator of GIAN and Head Center for Education and Technology, IIT Guwahati. Professor Niranjan Sahoo, Course Coordinator of the GIAN course and Faculty in the Department of Mechanical Engineering, IIT Guwahati. I request all the dignitaries to please come on the dais and have their seats. Please, sir.
Participants also get to learn from online.
As we begin this academic journey, let us take a moment to seek the blessings of the divine. I request all our honorable guests on the dais to proceed towards the lamp for lighting the lamp, symbolizing the illumination, knowledge, and wisdom. Please, sir. As we begin this academic journey, let us take a moment to seek the blessings of the divine. I request all our honorable guests on the dais to proceed towards the lamp for lighting the lamp, symbolizing the illumination, knowledge, and wisdom. Please, sir. As we begin this academic journey, let us take a moment to seek the blessings of the divine. I request all our honorable guests on the dais to proceed towards the lamp for lighting the lamp, symbolizing
ब्रह्माच्युत शंकर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्म विचार सार परमा.
Thank you all. Kindly have your seats. The GIAN course on Combustion Theory and Application is a timely program designed to provide an in-depth understanding of the course. Course Coordinator Professor Niranjan Sahoo and foreign faculty Professor Detlev Markus will share their knowledge and experience, ensuring an engaging and interactive learning experience. Now I request Professor Sukumar Nandi, Dean of Administration, IIT Guwahati, to felicitate foreign expert of today's GIAN course, Professor Detlev Markus, with a traditional gamosa and a memento. Please, sir. Thank you, sir. May I now request Professor Niranjan Sahoo, Course Coordinator of the GIAN course, Combustion Theory and Application, to deliver an inaugural address. Please, sir.
Very good morning to all of you. Dignitaries in the dais, Professor Nandi, Professor T. Bharat, Head CET, Professor Hazarika from Mechanical Engineering, and of course we both, Professor Markus and myself. So it's a great privilege for me to announce this course, which is being delivered through our GIAN portal on combustion theory and applications. So let me explain about the background or how we evolved about this course so far. So basically a team from PTV visited to our campus 2 years ago, and they were looking at the exploring the potential of renewable energy and other energy resources which can substitute the conventional fossil fuels. Through this interaction, we had a team from industry participations from the northeast regions, oil industries. So during that time, the PTV team along with Professor Markus visited to our campus, and we had one fruitful discussion during that time. And from then onwards, we started discussions of how we can make it a next generation course for particularly for the young and budding engineers, students who can make this concept be aware of. So the word combustion is derived from the primitive eras where we have simple wood combustions. But during that point of time, there is nothing the world called pollutions or any kind of climate change, and this combustion in fact was evolved few years ago as a fossil fuel combustions over last 100 years. But nowadays we have come to a stage that conventional fossil fuel combustion is no way reliable, is no way it has a potential to sustain for the future. So we have to come up some new alternatives that can cater the next generations. So through this concept, the word decarbonization, green combustions comes into pictures. So taking into those accounts, we try to initiate at the grassroots level for the next generation scientists, engineers, academicians to make the things aware that conventional technology of combustion is no longer valid. We have to look for the alternatives in the form of green energy. So this is the viewpoint or global aspects of how the course was evolved. So down the line we'll have variety of lectures. So basically our course structure is designed in two aspects, like fundamental theory of combustions, which are normally available in the classical textbooks, and but at the same time, and we also had designed some kind of measurement methodologies of combustion diagnostics, explosions, and where our foreign collaborator Professor Markus will take a key part in delivering those lectures. So in total, entire benefit of this course will be in the audience of mechanical energy, energy engineering, chemical science and technology. All these groups of people, will get benefited. So the course is designed for 2 weeks, starting from today, 25th November to 6th December. So in this course, we have planned quite a significant number of lectures, and of course, every day we have one tutorial sessions where participants or students, they can share knowledge. In fact, we are planning to have similar kind of presentations from their side, so that always there will be interactive sessions. So with this note, I conclude. I hope you will enjoy the stay and enjoy this course, and thank you for your attention.
Thank you, sir, for the details about the course. May I now request Professor T.V. Bharat, Program Coordinator and Head Center for Educational Technology, to deliver a brief about the program and the activities of the center. Please, sir.
Thank you. I'm thrilled to be here today to participate in the inauguration of first GIAN program of Phase 4. I join with my distinguished colleagues, Professor Nandi, Dean of Administration, Professor Shyamantika Hazarika, Head of the Mechanical Engineering, Professor Sahoo, the PA of this particular program, and also we formally welcome Professor Markus to IIT Guwahati and this particular GIAN program. And this is a very auspicious day to inaugurate the first GIAN program, and they are very highly competitive in nature. So you must have seen now from the address of Professor Sahoo that there's a lot of homework that has been done. 3 years of hard work, there's a visits that happened from there to PTB to here, and there's a lot of discussion that took place, and industrial involvement, all such things have happened. That speaks the success of this particular course itself. Highly competitive. We submitted around 20 GIAN programs from IIT Guwahati, and 10 have been sanctioned so far, and we are waiting for about 7 to get sanctioned. There are rejections and many other things happen, and a long review process, etc. And this speaks about the importance of this particular course, and also the meticulous arrangement of the sessions in 2 weeks. And also we have conducted these GIAN programs in number of phases from the Center for Educational Technology. The GIAN, Global Initiative of the networking, which is very important for engaging international experts in participating in the leveraging the Indian scientific and technological intervention, where the development aspects will take place through good collaboration from the international experts. This particular GIAN program, GIAN in Sanskrit it is called wisdom or knowledge, which actually provides a good platform for Indian students, scientists and everybody to participate and get engaged in scientific discussions, and we'll come to know the global perspective of certain topic. That is the best part, and which is initiative of Ministry of Education. We are in currently the Phase 4. The advantage of this GIAN program is that there are a number of participants who also joined online. We have to stream these programs, stream these sessions. So currently the streaming is also taking place, and audience can join from anywhere, and these recordings can be converted as NPTEL courses. So the NPTEL courses, you must be knowing that there are a number of courses currently available on YouTube for freely available. Also, if you want to get a credit out of it, and you need to register and also write exam to get the credits or certificate, and certificates can be converted to credits. This GIAN program, the 2 weeks or 1 week, that can be converted to, in fact, NPTEL. So this program also is hoping that we will convert to NPTEL later on. From IIT Guwahati alone, the CET Center for Educational Technology has developed 700 courses, and they're all up on YouTube. And this is a great initiative, and we are hoping that this will be a very successful program, and I hope we will have a lot of learning that happens, and thank you so much.
Thank you, Bharat sir, for the brief about the program and the activities of the center. Now, may I request Professor Samantamani Hazarika, Head Department of Mechanical Engineering, IIT Guwahati, to say a few lines. Please, sir.
Esteemed Professor Markus, Professor Nandi, Bharat and Professor Sahoo, and dear participants, it's indeed a great privilege to be here this morning and be present for the GIAN course on combustion theory and applications. We at the Department of Mechanical Engineering, IIT Guwahati, we strive to balance fundamental areas of engineering together with very emerging technologies. So this course is a result of that effort, and I am pretty sure that you'd gain a lot from your interaction here. But beyond this course, I would urge you to explore the possibility of interactions with other faculty in the department or in the institute and make the most of it once you're here. I, on my personal behalf and on behalf of the Department of Mechanical Engineering, welcome you all and wish you a very fruitful interaction in the days ahead that you spend here. Thank you very much.
Thank you, sir. Now may I request Professor Sukumar Nandi, Dean of Administration, IIT Guwahati, to say a few lines about the program and the institute. Please, sir.
Very good morning to all of you. My colleague on dais, Professor Hazarika, Professor Sahoo, Professor Bharat, and the esteemed guest in this program, Professor Markus, and all of you participants online or in presence. I welcome you all to this program. It is my privilege to be here. The first program, after a long time I am here. It is a little bit emotional because CET started with me in long time back, and this e-classroom, then the other things, initial creations, I was involved as CET head, and that time we were participating NPTEL course, the first set of NPTEL or NPTEL, whatever you can say, that course creations. I was NPTEL coordinator and head of CET, and we got these two buildings. This building, 2 floors, we have to do something. We are struggling to create our courses because we are not having any video recording facility, that to be created and all these things. Subsequently, things came up and we remodeled it, and now you can see we are in a good shape as far as recording is concerned, as far as delivery is concerned, as far as streaming is concerned, every aspect we have grown. So be it emotional here, but it's nice to see the things are in place. And during this period of journey, since 2004, lot of things happen in this CET at per se, and we have done lot of contributions in national level as well as international level. This is one of them. Coming to IIT is the 6th IIT, and in the series, the first indigenous development of IIT and creation of the IIT. Why I told indigenous? Because no foreign participants. Earlier 5 IITs, foreign participants were there. They helped a lot. This was creation our own. And subsequently, the other IIT came up. And till now, our IIT, we have lots of activities we are doing, considering the interdisciplinary nature, lots of interdisciplinary programs we have started. Today's program, I put it in the interdisciplinary nature because this needs chemical engineering, mechanical engineering, energy science and engineering, and so on, including today if you go to the combustions and other things, people say that combustion is doing some things and used in some places. the feedback mechanism and others comes there also. Some electronics and computer science comes in picture. And AI and machine learning is everywhere, because we learn the several things, the modeling. Today everything can be done in the simulation level, and lot of labs as well as classes. This course is also part of that. So it is amalgamations of several engineering plus material science. I am putting material science is also very important, because these things also from where we will get what and others is also important. Now today's scenario, earlier combustions and present combustions are huge difference, because today we cannot think of the earlier technology, earlier combustion mechanism, be simple combustions in our house, to the nuclear combustions or some other combustions. Altogether it's the scale is different, the requirement is different also, and as a result we should learn, we have to survive. Fossil fuel may not remain in long run, we have to survive, and how to use minimum fossil fuel to make it at more available for our future generations. So combustion theory and applications needs to be relook into it, and the guest here, the esteemed Professor Markus and our other colleagues will look into this, and you got opportunity to learn. Please utilize the options, interact with everyone. Also you have to remember that among the participant online or offline, the in presence, this interaction is more important than one-way traffic. One-way traffic never gives learning complete. Why? Because the lecture what is going on, the person thinking you are getting and trying to explain most of the things own way, but it may not reach to the your mind. Your cognitions is another important requirement. So you should learn in a better way. One of you ask questions or interact were benefit to all, but our nature is that better not to ask. But I request you, please interact. You will learn a lot. It's not required to go by theory one way or lab one way, just experiment given you are doing the lab. Learn as much as possible so that you can recreate yourself the such scenario. So hope this 10 days no? 10 days you will learn lot about this. It is our need, because we are doing fossil fuel, we are using alternate fuel, we are using alternate other options, renewable energy, how to combine them and make it more affordable for the everyone and success in our future generations. Hope you will enjoy this and expect something from this also in future. You people can be utilize this for our Indian need. With this, I thank you all for coming and attending and participating in this program. Thank you.
Thank you, sir, for the encouraging speech. Now may I request the foreign faculty, Professor Detlev Markus, Head of Department PTB Braunschweig, Germany, to say a few lines. Please, sir.
Yeah. So, dear professors, dear participants, so first of all I have to thank Professor Sahoo for organizing this course. It's my pleasure to be here. It's my second visit of IIT Guwahati, as explained before. And of course, the question is, why are we offering this lecture here? So one of the most important topics in our days is global warming. And global warming is directly related to the amount of carbon dioxide in the atmosphere. And this, of course, is related to the use of fossil fuels, as explained from the other professors before. And if we want to stop global warming and to stop the local climate change we face in different areas in the world, heavy rain in Germany or very hot summers here in India. We have to change our energy system. And here we do not have to replace only fossil fuels, we have to use other modern energy carriers, hydrogen-based energy carriers, ammonia, maybe iron. And with this, we have to consider efficiency and we have to consider safety. And both of these topics are related to the work of my institute, or the institute where I'm working, the Physikalisch-Technische Bundesanstalt, the National Meteorological Institute of Germany, and therefore I'm really happy to be here and to discuss with you in 10 days some of the new modern applications of combustion. Thank you.
Thank you, sir. Now may I request Professor Niranjan Sahoo to deliver the vote of thanks. Please, sir.
So at the bottom of my heart, I thank to all the distinguished guests who has come here by spend with their valuable times. Professor Nandi, thank you, sir. Professor Hazarika, thank you, sir. Professor Bharat, thank you, sir. And also Professor Markus, who was visited all the way from different country, Germany, to us. At the same time, I also give my sincere thanks to entire CET team for arranging this or planning for this course. From the last 2-3 months, we have been struggling to get the things done at various levels, especially Kaushik, Mr. Debjyoti, Mr. Kallal, and so many other staffs. And in the end, it is the participants who make this course success. So I wish all of you you will get this course benefited. And thank you for your valuable time, and thank you very much for this inaugural session.
With this, we come to the end of today's inaugural function. Thank you all. I request everyone to proceed towards the tea lounge for tea. Please.
I have to improve it. So I'll take the leave. Some examination is going on here.
काम नहीं करेगा? ओके, ठीक है, ठीक. या फिर कोई स्टिक भी होगा तो चलेगा. स्टिक है तो चलेगा. ठीक है, बाद में देखो. Okay. So anyway, good morning to all of you. Okay. So before I start our lectures, let me tell you the background. What is the expectations? What are the things that are going to come out? How you people are going to get benefited in a kind of win-win model situations, which is beneficial for you, for us, and that way. So as far as this course is concerned, take it as if you are taking it any conventional course during your classroom. Don't think that it is a very high level course. It is, and how you can get benefited based on the outcome for this course. So the entire intention for this course is that just to give you the brief insight about the basic theory and what are the innovations or the things that is the need of the hour. So for the time being, what my part of the lecture, I will try to keep more or less conceptual things about this course, which is mainly on combustions. Many of the stops they are available in the textbooks, as well as you can find in this line. There may be many courses which are available online through NPTEL platform. But the other side of the story of this course is that how you can get maximum outcome from our interaction with our foreign expert, which is Professor Markus, because he works in the area where the combustion with a new technology, that is the demand of the hour or need of the hour, and how you people can train yourselves just to get out of the conventional method of combustions to higher end or the next generation combustions. Last 100 years, the when you deal with this combustion process, we never bother about pollution, emissions, because hardly you will find one or two few vehicles running in the ground, and there are very limited applications where the combustion was fossil fuel was the need. But over last 100 years, the transport sector has grown to such a level that we reach in a situation that we say that fossil fuel combustion is no longer a standalone technology for futures. So you have to go for the future generation methods where we can run our systems, energy sectors, without intervention of degradation of environment, without intervention of pollutions, air pollutions, without intervention of cutting woods, trees, all these things. So this is a kind of a need of the hour, and another big issue of this combustion is because the all fossil fuel combustions are they are carbon based, and when there is a carbon, obviously, and our classical stuffs have already demonstrated or already proved that we are end up with NOx, we are end up with CO emissions, and we are, because of these emissions, there is a detrimental effect of our pollution effects across the globe. Okay, this is the background of this course, and what we have planned is that we will, for most of my lectures will be based on the standard conventional theory. I will try to give some insight what research can be done on this particular area, what are the different level of research that we can think of. Some of the things which are already available in the textbooks, but still we do not pay attention because it is not in our course curriculum. So, some of the things also little bit of mathematics involved, where you need the analytical modeling of combustions. So, this so that way the lectures are designed and planned, and Professor Markus' lecture will be mainly on the hands-on practices with various of mainly with combustion modeling packages like Cantera and other things. Other thing is that this is similar to a kind of CFD normally we call in fluid mechanics term. But all these fluid mechanics packages, they cannot handle combustion modeling, and some people also look for the high end combustions, where we talk about dissociation effects that comes in the area of rarefied gas dynamics, where dissociation effects comes in, where that is normally used in the ramjet and scramjet engines of aircraft engines. So, those kind of concepts, there is no standard technology or standard modeling is involved. So, the aspects are like this: we start with some analytical modeling and end up using some standard packages, then later part we move on to experimental data. In the experimental data, diagnostics also plays a very crucial role. What are the measurements you are going to make? Is it doable? That is the another chance. If doable, what are the instruments that is available? All these sorts of questions you need to ask yourself to perform these experiments. And the combustion experiments are such that you deal with a kind of the situation could be a controlled combustion or uncontrolled combustions. Uncontrolled combustions create a very unavoidable situations, but if you can do controlled combustions, it can do miracle. Means like we in the transport sector, when you travel faster, ramjet, scramjet engines, they are like a supersonic mode of combustions. So, that way you can travel at almost 5-6 times of maybe 12 times Mach 12, 10, 12 Mach number you can achieve for your vehicle. So, it starts with wood burning and there is no end, but till now we have reached to a level of rocket combustions. So, this is the broad domain, and in this domain we are catering so many things, starting from analytics to modeling to the experiments. So, that way if you look at your course schedule, we have designed all about close to 28 to 30 lectures. Additionally, there will be some tutorial sessions. So, we will try to see how best we can go ahead with that. So, in the first lecture, it has nothing to do with the word combustions, rather to start combustion, what background exercise or background topics you need to look at. One thing anyway, you have to do the thermodynamics. So, here I will talk about some glimpses or terms that are associated with thermodynamic concepts and all. So, it starts with basic thermodynamic modeling, then zeroth law. Then when you talk about thermodynamics things, we have to see that the system has to be defined, that we call as a hydrostatic systems. It's a simple compressible systems. So hydrostatic word comes into picture. It's a hydrostatic is a broad word, which includes liquid plus gases. But when you move it to compressible systems, then it becomes only gas. Then the thermodynamics also deals with energy interactions from variety of sources. With thermodynamic viewpoint, we talk either in terms of work or heat. So those form of energy interactions, we call this as a modes of heat transfer. Then we have this to deal with thermodynamic system very closely, or if you can model it in a quantitative manner, then you have to define the systems in a quasi-static process, which is the infinitely, which has to undertake with its slowness. Then we dealt with laws of thermodynamics, then Carnot cycle, reverse Carnot cycle, and based on this we come up with temperature scales, where how the Kelvin scale was evolved over the entire history. Laws of thermodynamics also gives variety of thermodynamic parameters, properties, and one such property is entropy, which plays key role whether a system is reversible or irreversible. That is what the entropy word comes into picture. Now, having said this, when we have entropy, then another term that drops in exergy and second law efficiency, which basically talks about any source of energy which what you have, what is its corresponding work potential. Okay. Now, this particular entropy and exergy term actually is very vital for all kinds of combustion modeling. Probably down the lectures, when you see, you will find the definition of entropy based on chemical terms. So main system that we look for when you deal with this, the term, the significant term that we come across in this thermodynamic course, that will be actually used in their applications. One basic things in the thermodynamic system is that, for example, when you, for example, for in a simple analyzing a simple systems, two gases mix or two fluids mix, then it gives the third systems. So when you analyze this as a mixture, we know what is in, what is out, and we have all the parameters known to us in the beginning. But when you do the combustions, because you do not land up in having them same mixture is out, because we have a fuel and we have air, but at the end of the day none of this thing is there in the output, because it has died down in terms of some combustion products. So quantification of each term is dependent on the main source, whereas the common conventional mixture, it is not that, because mixture when it comes out, it has same identity, some identity which is in the in which it gets mixed, but there is no identity when it turns out to the combustion products. So while modeling, either in numerical modeling or experimental things, the cause and effect things comes into picture here, because effects are because of certain input, but that input you might be knowing, but that does not give the some identity which remains with that input. So that way the combustion products, what it will come, you do not have any knowledge of that. So that way the calculation of entropy is and exergy is very vital, because we do not have any identity of main input. And then we have the second law efficiency. So, to have effective combustions, quantification of this term is essentially a main requirement. So, to give the introduction of these things, and this is something like basic knowledge, that we have some kind of systems, we have some kind of system like this, where we talk about three methods of energy conversion: electrical to mechanical and vice versa, electrical to thermal and thermal to mechanical. So, that way things can happen, but to make these things happen, we require the energy sources starting from solar, geothermal, chemical, nuclear, hydro, all these things take part. Now, when for combustions, our main attention remains with this chemical fuel, and that is one part of energy interactions that we have to make. Means our main focus would be on this, mainly from the fossil fuel combustions. Other parts are kind of a visualization of next generation combustion, we call as a green combustions. It could be, many people call this nuclear, hydro, solar. They are harnessing energy from renewable sources to get the benefit out of in terms of electrical power or mechanical power. But at the end of the day, our main output is electrical, and we can get the conversion of mechanical output in terms of soft power by running a vehicle. In terms of household applications, it can be electrical, it can be cooking, so many varieties. So, that way linking of this activity is very important. Now, coming to the basic terminology, I do not have to say many things, because they are textbook stuffs. We have system, surroundings, and when you model this, we call this as universe. And the system, while talking about system and surroundings, the thermodynamic viewpoint says that either it has to be a macroscopic approach or microscopic approach. Macroscopic approach takes as a whole, which normally we deal with analyzing thermal systems. Microscopic approach becomes very significant when you deal with combustions, particularly to the case when you go for reaction modeling, where species try to dissociate. For example, at maybe 800 to 1000 degree Kelvin, nitrogen starts dissociating. Close to 4000 Kelvin, oxygen starts dissociating, and maybe if you go to 8000, 10,000 Kelvin, we will have, during this period also, we have NOx formation, carbon monoxide formations. But if you still go ahead, then we land off having further dissociations at molecular level, atomic level, then atoms becomes ions, ionic level. So, all sorts of things that comes into picture, where macroscopic analysis of thermodynamics has no role, and we have to deal with in the angle of microscopic approach, talking about species, atomic level, species formation as a whole. So, this is what we say new generation combustion modeling. And talking about this, we have systems, we have closed systems, open systems. Closed system says that there is no mass, no energy interactions, but energy interaction is possible. But when you deal with the open systems, both mass and energy interactions is possible. Now, moving further, the evolution starts with the zeroth law, and when you talk about zeroth law, it talks about thermal equilibrium. There we start off the words using the diathermic wall or adiabatic wall. Adiabatic wall says that adiabatic wall means the no transfer of energy in the form of heat with others, which means system does not allow to get into equilibrium, because suppose you have system A, B, C, we have a diathermic wall in between A and B. So, that means there are possibilities that energy interaction can happen in both ways, but if you have an adiabatic wall, this and this cannot be interacted, and this A and C cannot be interacted. Similarly, B and C we cannot interact. So, system C can never be in equilibrium with A and B. So, with that concept we call it that the word thermodynamic equilibrium comes into picture, where the zeroth law says that if two systems are in thermal equilibrium, then it will also be equilibrium with third systems, unless and until they are separated by as long as they are separated by a diathermic wall. The word zeroth law has some historical significance. It has evolved after the first law. So, during that, so that is the main purpose that it was told as zeroth law. Then moving to the analyzing thermodynamic systems, initially we call this as a hydrostatic systems, which takes care about liquid as well as gas while modeling, but we can bring down to a level where if you take particularly for ideal gas situations, gas modeling, then you can call this as a compressible systems, where three different parameters, pressure, density or volume and temperatures, they comes into picture, and all of them has to be kept in some thermodynamic coordinate systems. Here I have put this x and y, x dot, y dash, just to give that it can be of any x and y, they can be of any thermodynamic property. Then coming back to modeling of these thermodynamic systems, if you look at the mathematical representations, for the time being let us say that we have three parameters: pressure, temperature, density or specific volume. They have to be related mathematically. Then what we can write is that, let us say volume, it can be pressure, function of temperature and pressure, or if a temperature, it can be represented as a pressure and volume, and if this is the functional relationship, we can come out of in terms of mathematically in terms of partial derivatives. Through this expression we can find dV change in the volume, we can also find dt change in the pressure. How do you measure this mathematically? Keeping one parameter constant, we try to measure. So, this is the mathematical way of representations. So, these two equations we are using. Now, here we have to see, then we have to see whether our system is in liquid or gas. Accordingly, we can play with these parameters. Is there any change for because for liquids we require two parameters, either pressure or volume, because they are interrelated, but gas we have to define three parameters simultaneously. So, that way the understanding of our or representation of these equations has to be changed. So, this is exactly what we are going to do for our writing the combustion equations in the analytical equations during our combustion analysis. And while talking about hydrostatic systems, we define the terms which is actually the properties of the medium or the gas or liquid that we are going to say. One is volume expansivity, isothermal bulk modulus and isothermal compressibility, then volume expansivity and isothermal compressibility. What it says that it actually by definition you can read it out, but what I am trying to say is that these terms which is like beta or kappa k, and there is another term which is relation k and b, they are reciprocals. So this, if you look at these equations, let us say we talk about beta. Beta stands as volume expansivity. It talks about change in the volume with respect to change in the temperature, keeping pressure constant for a given working given fluid, and that way we define beta. Then we have this isothermal compressibility kappa, which is K, with isothermal compressibility K, which is defined by 1 by B. So that way we can modeling it, and here as I told, if it is a these two terms allows you to, these are the fixed properties of the material or the fluid, but these two properties will tell you change in the pressure with respect to change in the temperatures. This just to give you a glimpse that there are mathematical formulas that do exist which can give you the correct information of your in finding the properties. Then we move on to the classical definition of modes of energy transfer. Either we call this as a work or heat. When you say work, it means that we view these systems to be rising and falling a mass against gravity. So it could be electrical work, it could be any form of energy interactions. It can be electrical energy, it can be magnetic energy, it can be any nuclear energy. But when you actually thermodynamic viewpoint, when you call this as a work transfer, it can be visualized in a sense that we can raise or fall a certain mass against with respect to gravity. And if you cannot interpret as it work, then you have to interpret in terms of heat. So if it is a heat, there has to be a temperature difference. So that way the evolution of heat and work comes into pictures. Then coming to the heat transfer. Heat transfer has three main sources. One is conduction, convection and radiations. Conduction's laws are governed by, conduction mode is mainly solid medium, it is governed by the Fourier law. Convection and radiations, convection mode is liquid and gas medium, and radiation will be gas and vacuum. So accordingly these are three laws of convection, three laws. One is Fourier law, second is heat convection, and third equation is Kirchhoff's law, Stefan-Boltzmann's law for radiation. And these radiation terms becomes significant amount which we say energy interactions when you go in the areas of high-end combustions, where temperature you can expect more than 8000 or 10,000 Kelvin, where dissociation effects or rarefied gas dynamics effects come into picture. But in our conventional practice, at lower temperatures, we enter into either combustion or convection. Then coming to the quasi-static process and work transfer. To analyze the work transfer, we have to define a system, and its system has to be specified either in variety ways. One is by giving some name into that process, either isothermal, adiabatic, reversible adiabatic, constant volume process, constant pressure process, and they can be of traced in a pressure volume coordinates, in which work transfer is possible through this integral. That is most important. That means we can, once you define this path, we can actually integrate this pressure volume diagram to get the work transfer. So, these are the standard expressions for variety of work transfer in various processes, starting from isobaric, isochoric, isothermal, adiabatic and polytropic. Now, coming back to the laws of thermodynamics, and having said that work and heat, these are the two modes of interactions, and if you take a audit of heat in a given systems, if you can actually say whatever form of energy that system interacts, we can put in that gross domain of work transfer or heat transfer, but then whatever, either it can enter into the system, it can go out of the system. So, if you take a stock of it, what is coming, how much coming and how much going, not necessarily that both should match. Now, if it matches, that is well and good. If it does not match, then how do you quantify it? So, that is the reason the term, the difference between heat and work was proved to be the fact. It gives a term which is UF and UI. U stands as internal energy, which is initially at the when the system is at the beginning, and final state we say F, and they, for an hydrostatic equations, heat, work and internal energy, they get they fit a relations. And again with same mathematical notations, the internal energy U we express in terms of the other parameters as well. It can be related with a temperature volume or temperature pressure. So, based on this we say that whether the system is a closed systems or open systems, and when it is a open systems, we define the term enthalpy, when it is a closed system as a flow energy, and when it is a closed system, it is the internal energy within the system, which is internal energy. Then coming back to this is about the overview of first law, and coming back to the second law, there are few silent features of this second law that many books talk about. Now, when you talk about energy, either heat or work, the first law does not talk about the word heat or work, it talks about the quantity, whether 10 kilojoule, 20 kilojoule, whether 10 kilojoule of work or 20 kilojoule of heat. It does not use the word, it just take a stock of energy auditing, just a balance and difference between these two, it gives the in the form of internal energy. But when you come to the second law, it really quantifies, then why we say it is a work and why it is called this as a heat. So, that way quality of the energy comes into picture. Now, come another important significance for this second law is that either work or heat, one can think of the conversion of work to heat or heat to work. So, question arises whether 10 kilojoule of heat can get converted to 10 kilojoule of work, is it possible, or reverse 10 kilojoule of work to 10 kilojoule of heat, is it possible. So, all these questions were answered. That way the energy transfers were categorized in two forms, one is high grade or low grade, and work is always treated to be high grade and heat is taken to be low grade. So, what it says is that complete conversion of high grade to low grade is possible, low to high is not possible. This is one thing, and if it has to be converted, then what is the mechanism that we have to evolve. So, this is one way of answering the second law. Another point is that, and if it is converted, what is the upper limit? How much percentage of work that can be converted? So, all these answers were taken into account. And third most important aspect is a kind of a energy dispersions or energy spreading, or we say that can you localizely store energy on its own at one particular locations. For example, if you put water at, maybe water always flow from high elevation to lower on its own without any constraints, but its reverse does not work out, because that is the law of nature, that is the that way we say that localized concentration constant energy has no value and it has to spread. So, the spreading when it spreads, its own identity is always lost. So, and that spreading, because of this spreading, the thermodynamic gives a term which is called as irreversibility. And this irreversibility is further linked to entropy. How do you quantify this irreversibility? In terms of entropy. And another point is that when you deal with first law and second law, one thing we say, the entire analysis is based on the system and system within the systems, whether the process is reversible, irreversible, and we normally do not bother about what is happening into this immediate surroundings. For example, if there is a burning of fire, in this immediate surrounding you can feel its effect, but to the down the line some other location you may not feel that effect. That is because because it does not have that intensity to propagate further, which means that is the word we call, the term is exergy. So, the word exergy says that when you analyze a systems, you take its advantage, you take its effect with respect to its surroundings, and when you take about this, analyze the system with respect to surroundings, then you have to quantify in terms of exergy. So, there are modeling of exergy which is already there, and here that those things are not direct relevance to our course. One is like a heat engines, which says that how if there is a mechanism of energy transfer from heat to work. So, you have to use this concept of heat engines, which is a cyclic device which has to work in a manner, it takes heat from a high temperature source and it has to reject to give certain amount of work. So, this is what the mechanism of getting work or getting a high grade energy from a low grade source. The other side, if the work gets consumed, we can say either we get the cooling effect. The cooling effect can be of refrigerator or heat pump mode, and these are the some statements of second law statements based on the Kelvin Planck statement, which is with respect to heat engines, which says that it is impossible for a device that operates in a cycle to receive heat from the single reservoir and produce net amount of work. And the Other side of the second law statement is on Kelvin statement, which says that it is impossible to construct a device that operates in a cycle and produces no effect other than heat transfer from lower temperature to higher temperature. So, this is about heat pump and refrigerator. Then something on Carnot's and reverse Carnot cycle. So, for the second law was evolved with a viewpoint that how do you define a that heat that cycle, either heat pump cycle or refrigeration cycle, in such a way that what are the thermodynamic processes that needs to be involved. So, we have a reversible isothermal process expansion, reversible adiabatic expansion, reversible isothermal compression and adiabatic reversible adiabatic compression. So, compression what means it takes as some work is taken as input, expansion stands as work as output, and the reverse mechanism we call this as a Carnot refrigeration cycle. So, based on that we can draw pressure volume and temperature entropy diagrams. So, that way we can quantify how much heat or how much work transfer that takes place. And these are the some terms, parameter terms. We talks about the quantification of Carnot and reverse Carnot cycle for heat engine and refrigerator or heat pump. And another significant inference that Carnot cycle gives is about definition of a new scale. So, prior to this, whatever thermodynamic scales we are using, either it is a 10 centigrade or Fahrenheit, and the measurement of those temperature value based on the kind of based on the kind of fluid which actually measures the temperatures. So, here we use the word it gives a another scale, we call this as a Kelvin or Rankine scale, and here the measurement is based on this Q and T, and in between there is a functionality that relates. That functionality happens to be a linear function, and as long as this temperature is expressed in a Kelvin scale, we can directly relate Q and T by this linear equations. This is another significant development that we come across. Further, it gives the definition of absolute zero. So, if I say 0 degree centigrades, it is a freezing point of water, and that freezing point was treated as a benchmark or reference, but below that it is possible -2, -5, -20 degree centigrade is possible, but there is no concept of minus 10 Kelvin, because that is the thermodynamic limit that puts. So, absolute zero till date it is not reachable, at least with our planet being the reference, and when you have absolute zero, it gives a kind of a means there is no disorderness in the systems, there is all the molecules become standstill and there is no kind of energy interactions, either work or heat is possible. So, it is a completely static or steady systems. So, what he says, if that is the case, that point of absolute zero, entropy vanishes. There is no definition of entropy at absolute zero. Okay. So, to quantify this, we have there are different to quantify the irreversible nature of a given systems. We have to do in kind of some kind of modeling. What we talk about, one is thermodynamic equilibrium of chemical systems, other is how to include the dissipative effects, and these two terms are very vital when you actually do the chemical reactions during a combustion process. So, these two are going to be used in our combustion systems. So, this entropy word I have told so many things that how the entropy is a very classical term, but it has a thermodynamic viewpoint says that entropy of system always increases, and further when you talk about chemical reactions, so reaction has to proceed in the direction of increasing the entropy, which means that is the only parameter through which you can judge a chemical reactions, because of your fuel we have air, and then when they mix together you find their initial entropy, and if at all there is to be combustion products, to down the combustion products when you actually calculate their entropy, you must see that entropy should be higher when the reaction proceeds. So, that is the direction of increase in the entropy, or entropy generation is also a measure of irreversibility of a given process. So, these are the some classical expressions. If the process is a reversible process, we say in a solid line. If the same process is defined from an irreversible manner, it is shown as a dotted line. System goes from 1 to 2 in one direction, and system comes from 1 to 2, and when it is a reversible, which means that when we have initial state 1, we can go to 2 in a reversible path, and if you also there is a possibility that we can come from 2 to 1. But when such a system is defined in an irreversible path, one way direction is possible, reverse is not possible. So, that way we come up with the equation called as Clausius inequality, and it gives the fact that entropy of an isolated system always increases. And for irreversible path, we have this term which actually quantifies the what is the entropy generation. These are some of the equations that are used to calculate the entropy for a gaseous systems. Talking about using the gas equations, ideal gas equation PV is equal to RT, one can find the change in the entropy from its state coordinates, either temperature volume or temperature pressures. Now, coming back to another significant term, when we say exergy, which actually quantifies what is the work potential of energy. So, if you have a systems which is quantified as a total energy, this total energy can have multiple parts either in the form of work or heat, but actually when you see for these systems, exergy potential is only certain portion. That means, if you say 10 kilojoule of energy which is constrained in a systems, its exergy potential cannot be 10 kilojoule, it has to be less than that. Now, when you do this and that less than that is not because of our system issues, it is mainly because the nature of energy has to dissipate, which is not recoverable. So, we call this as a unavailable energy, which is due to irreversibility in our nature. So, whatever most efficient system if you do, even then there will be some energy which is not recoverable. Now, this energy, how it enters to a system, it can be come from mass, heat or work, and each will have its work corresponding exergy potential. So, exergy can, that means in other word we say exergy can come through mass, it can come through heat or it can come through work, but each will have when it goes out, it will have its corresponding exergy output. So, that way the total energy never matches here. So, in that sense we can change is that is the exergy change for the system and which is exergy destroyed. And this exergy destroyed is nothing but your unavailable energy. So, this is how you link the overall, this gives the when you in many systems in our research study we do particularly in the when you deal with engine analysis, we talk about energy analysis, but it is better that if you do exergy analysis, because that will give you the real picture by analyzing the complete thermodynamic viewpoint in terms of energy which is getting wasted from the system. So, this is what something like that, how do you calculate this exergy. So, you have for closed systems we call this as non-flow exergy, for open systems we have flow exergy. So, exergy from mass, heat and work, we will have expressions. So, they can be found out keeping surroundings into pictures. How that surrounding, so exergy destroyed, why it comes? Exergy destroyed means entropy increase. So, if you look at this term in both the equations, either non-flow or flow exergy, there is a term exergy which is destroyed, which is defined by T0 into S2 minus S1, and here also same thing, same term appears in both the expressions. So, T0 stands for the surrounding temperature and S2 always increases. So, these two terms is always a positive quantity, which means that even though you are calculating exergy, this term takes away some part of it. So, that is the reason exergy destroys. And based on these laws are formed with respect to exergy reversible process, there is no exergy destroyed, irreversible process and impossible process. For any system natural occurring processes, we need to have destruction of exergy, and we cannot claim any processes which for which exergy is destroyed is less than 0. And this is one way that to quantify another term that comes in. One is efficiency, what we define while talking about heat engines based on this either Carnot cycle efficiency or in terms of heat transfer. Here it is mentioned in terms of heat transfer. So, there are three parameters involved here. One is best with respect to these heats, one is Q1, Qs and Qu. Qs enters to the systems, Qu which is actually utilized, Q1 goes to the surroundings, and this surrounding town number it depends, and if you actually calculate what is the Q in terms of the expression from the Carnot cycle, this turns out to be this. That means, when you talk about exergetic efficiency, work potential of this Q u is here, work potential of Qs is here. These expressions are nothing but we get the relations from the Carnot cycle, and finally it turns out to be exergetic efficiency in terms of the system efficiency. So, these two things are correlated, which says that exergetic efficiency is always also lesser than the your efficiency of the system, which is the conventional, the way the efficiency are defined for heat engines. Normally, this exergy efficiency we also called as second law efficiency. And finally, I just want to give some emphasize a realistic work, some kind of a comparison how you view exergy and energy in a manner. For example, when you if you look at only this part, it is some kind of arbitrary systems in which some energy in terms of heat enters and some energy in terms of work it produces, system produces, and while doing this some mass flow which is entering and is carrying some energy into it, and something mass flow that takes out some heat. So, what the significant term, I just kept some numbers, is that suppose it is 90 which is entering in terms of Q, flow and energy which is entering into the systems either through kinetic energy, potential energy or enthalpy or flow work, which is 10. So, total entering is 90 plus 10, 100, and here also you have here 40 and your work output give you 60. So, if it is a completely first law analysis, the energy auditing comes into picture 100 and 100. Now, even though you introduce internal reversibility within these systems, this 100 kilowatt could be lesser than that. So, that is based on the first law and second law analysis. But when you represent in terms of exergy, and even though and to make your system efficient completely, if it is 100% efficient, we will have 100 kilowatt work. I mean energy auditing we can achieve by introducing RGF, that system does the you use the system to work in a manner that it is a very small process, steady processes without involving all the instruments or mechanisms or devices. They work in a very efficient manner, which is doable with 100% efficiency. But still then, if there are some internal irreversibility comes into picture, for example isentropic efficiency for compressor, turbines, if you define those things, it will be little bit lesser than that. So, whatever may be, this is the energy auditing or balance between from the first law and second law. But when you actually convert their work potential to exergy analysis, you will find that although you are giving 90 kilowatt of work heat entering into the systems, its exergy potential is actually 60. If you have shown you the equations, you can calculate. You can be always less than that, because that term T0 into S2 minus S1, and for each term there will have exergy potential of enthalpy, exergy potential of this E which comes into picture, EFE which is comes out of this thing. If you take out its exergy potential, although it is 10, it is actually it could be less than that too. And even though through this process, and of course one thing is sure, since it is a work, its corresponding exergy potential will be same for this thing, because it is a work. So, these two remaining same for both the cases, and if we recalculate the same term in terms of exergy, you will land off an analysis called as exergy analysis, which says that exergy destroyed, there will be always exergy destructions, and that can be quantification. Why it is required? Because exergy analysis is very vital for any kind of analysis, thermodynamic modeling analysis for any kind of system. Okay. So, these are the some of the things that I need to talk about, and of course, in these lecture notes there are some problems which I need not have to describe explicitly I have to talk about here. Maybe there are some review questionnaires. When you share these slides to you, you can actually try to revoke or do some analysis understanding for this kind of simple problems, that those things we can take off in these tutorial sessions. These are the some problems. I will try to see if it can be done towards the end of our session. Okay, so this is all about my part, and maybe if you have any questions we can share, or maybe after that we can start our next lecture. Okay. Okay. So, Professor, you can take a lead. So, thank you for your attention. Now, I will hand it over to our Professor Markus. Either you can keep it in your front pocket or back pocket, wherever you choose.
Before I start with the technical details here, I would like to start with a very short introduction of my person and with my background and my motivation to be here. So I have studied chemistry in Bielefeld in Germany and received my PhD in mechanical engineering at the University of Stuttgart in 2002, and I'm working now for over 25 years, nearly 25 years, for the Physikalisch-Technische Bundesanstalt. That's the National Meteorological Institute of Germany, which is comparable to NPL, National Physical Laboratory here in India, which is located mainly in Delhi. So we deal at PTB with the art of measurement. If you have to measure something, which is then based on the SI units, this is related to work in Germany, which is done at PTB. And I'm head of the Division 3 at PTB. So in this division, 200 people are working on the field of chemical physics and explosion protection. So beside other topics, we also have to consider energy efficiency here and safety issues if you deal with combustion. And so this is my motivation concerning the topic we are discussing here. But of course there's another motivation. So last week there was an interesting article in one of our newspapers about people from India working in Germany. So this number has increased from around 23,000 up to 130,000 in one decade. So Maybe some other countries like US are closing their borders, but there are collaboration projects between India and Germany, so that people from India can come to Germany and work there. And what was really surprising for me, that the average salary of the colleagues from India in Germany is higher than the average salary of the Germans. That means mainly people with high qualification come from India to work in Germany. That's one important topic. The other topic is we have 50,000 students from India at the German universities. And I have worked with students from India a lot, master's thesis, bachelor thesis, and so on. And the last example was a female student who has written a thesis about ammonia combustion in my lab, and now she is starting a PhD work at TU Braunschweig, not in my institute, but in an institute at TU Braunschweig, again dealing with the usage of ammonia as an energy carrier. So there is a strong interest to have better cooperation with Indian institute like IIT Guwahati, for example. And to close this, my first PhD student I hired 2002 came from IIT Chennai, and so he received his PhD in Germany, also at University of Stuttgart, and now he's a professor at the Indian Institute of Space Science and Technology in Kerala. And two of my colleagues have visited him last week, so we have a project on ammonia combustion again. And I hope in the future we may have a collaboration with IIT Guwahati and a research project together. So this is my main motivation. But another topic is, of course, talk about fundamentals of combustions mainly related to the change of our energy infrastructure away from fossil fuel towards renewable energy carriers, hydrogen, ammonia, and so on. And when we have discussed, Professor Sahoo and I, when we have discussed about the topic of this program, of course we have to deal with the fundamentals, like in the first lecture, fundamentals of thermodynamics. Now we have to talk about fundamentals of the combustion kinetics. But we have to be, it has to be clear that we just discuss it very briefly. Of course, there are special lectures for each of the different topics. So we have numerical combustion, we have combustion kinetics, and so on. So the main focus at the end is renewable energy carriers and safety issues using these. So first question is, are there any chemists here? Has anyone a strong background in chemistry? Or mainly mechanical engineers? Yeah. So when in Germany, mechanical engineers, when they deal with combustion engines, they are looking at the efficiency. So horsepower, that's the important part. And the combustion process is, okay, it takes place, but it's not so of interest. But when you look at the combustion process, of course, it's chemistry. This is pure chemistry. You have fossil fuel, like gasoline. At the end, you have carbon dioxide and water, and unfortunately, soot and NOx formation and so on. This is pure chemistry, and you just use the energy which is stored in the chemical molecules to produce heat and power. That's it. So the engineer is interested in transferring the energy, and the chemist is maybe interested in the combustion kinetics, but of course we need both here to understand this process in detail. I have given here some literature, and when we look at online courses, and so one of the ideas of this GIAN course is also to have online lectures available. Of course, there are really good online courses. One example is here the Combustion Summer School at Princeton University. So these courses you can also find at YouTube, and really good experts talk there about similar topics. So motivation concerning combustion chemistry. So you all may know the Bunsen burner, where you use normally natural gas, methane, and this is burned with air. And you know that you have a screw at the bottom of this Bunsen burner, and the idea of this screw is that you can change the concept of the burner. It's quite simple. If it's closed, you have a non-premix system, you have a flow of methane, you have a flow of air, and the combustion takes mainly place at the boundary between these two flows. You have a non-premixed or classical diffusion flame. It's not so efficient, and this you can see here. It's a quite yellow flame because we form a lot of soot molecules. So the flame temperature is not so high, and this yellow flame stands for soot molecules, which burns later on. And then if you open the screw and mix the methane flow with some air, you change the flame behavior towards a premix flame. You have a very efficient, very located flame region here. So from this unstable, flickering yellow flame, you change it to this blue flame, and maybe if you have ever used a Bunsen burner, you can hear it also, that the efficiency becomes better when you go to this Bunsen burner flame or this premix flame. And what is also important, the color is changing. Here we have more soot, giving the yellow color, and here we have mainly UV blue radiation from CH radicals and so on. So it's the same mixture we are burning, methane with air, but it's totally different. And this is, of course, depending on the change of flow configuration, which then has a big impact on the chemistry which takes place at the end. And another motivation, this is then my background, safety. So here we see a BLAVI, boiling liquid expanding vapor cloud explosion. A tanker filled with LPG was in a fire and then exploded. And you can see here some houses. So the flame ball we see here has maybe a height of several 100 meters. And what is important, such a big flame, that such an accident always starts with a small ignition event. So, and to understand ignition, of course, you have to consider then again combustion chemistry. Otherwise, you cannot describe all the details here. So these two examples may have shown that combustion is a complex interaction of physical processes and chemical processes. So we have fluid dynamics, heat and mass transfer, thermodynamics, and chemical kinetics. And to describe combustion properly, we have to consider different properties, so stoichiometry, heat of formation, heat of reaction, just some few examples. Then we have different flame types. So we have this classical premixed flame. So here we ignite on nice video. Just a second. So we ignite a premixed here propane air mixture in the center of a vessel, and you see at the beginning a classical laminar flame which is expanding, and then at the end you see this wrinkling and you have a turbulent flame. So when we consider premixed flames, we also have to consider deflagration or detonation, so either subsonic combustion, mainly to diffusion, molecular transport and thermal conductivity, or detonation, so supersonic combustion propagating through shock, adiabatic compression. We also have non-premixed flames, maybe in classical examples here the candle flame we see, and of course we can have, especially in technical applications, something in between, so partial premixed flames, triple flames, and so on. So to explain this detonation, again, so here we see an colored Schlieren image of such a detonation. So here we have a shock wave in this area, and this shock wave compresses our unburned gas mixture, and due to this compression, of course, we have an increase in temperature, and if everything is working properly, this increase is strong enough to ignite the mixture, and then at the end the flame can propagate with a sound of velocity through this gas mixture, and so the flame propagation is much faster in a detonation, and which is also very critical for safety issues. When we consider a normal deflagration, we have a pressure rise of 10 bar, or 10 times the initial pressure. The detonation, we have a pressure rise up to 100 times the initial pressure. And when we then look at this DDT, deflagration, detonation, transition, there we can reach much higher pressure, so 150 bar, 200 bar, which then of course is difficult to handle if you have this in a pipe or somewhere else. So to show you some examples, hopefully these videos are working. So here we have a stoichiometric methane air mixture, and so it's ignited here at the end, and you see the flame is propagating through this tube, and at the end you can see the interaction of the flame with the gas flow, so this oscillating flame we see. we can also have a look at a detonation here. So the ignition starts somewhere here at the left, and then it accelerates here. The detonation takes place, and it continues as a typical detonation. As I've said, we have much higher pressures here, and here I show you some examples with a pipe made of plexiglass. This has a burst pressure of 140 bar. So it's quite solid, but here we use propane air mixtures. So the ignition again starts here, the flame propagation. The flame accelerates, and now there's the DDT, so the transition to the detonation. And at this specific point, the pressure was so high, you can see it here. The pipe was destroyed, and could not, because it could not withstand the explosion pressure. So maybe one. Okay, so here we see the images of this video. So the flame accelerates, and at the end it has a velocity of 2000 meters per second. So coming back to the fundamentals. So the chemical reaction we have to consider, for example, methane plus oxygen in air gives carbon dioxide and water. So quite easy. And if we look at the fundamentals, okay, the atoms are conserved. So we have one C here, and we have one C on the other hand, and so on. So we always find the hydrogen atoms and oxygen atoms and so on both sides. Of course, the number of molecules are not conserved. So here methane is changing towards carbon dioxide and so on. Then we have to consider stoichiometry. So we have propane, which burns then with air. So in this case here, 5 quantities of oxygen plus nitrogen gives then carbon dioxide and water, and of course nitrogen plus heat. So the ratio here is then of course important concerning the stoichiometry, and if the air-fuel ratio is correct, we can have a fuel equivalence ratio of 1. So we have stoichiometric combustion. So all combustibles and air or oxygen molecules are then consumed. But of course, if we have not enough propane in this example, we have a fuel equivalence ratio smaller than 1. We have lean mixture, lean combustion, and on the other hand, if its phi is larger than 1, we have rich mixture, rich combustion. In Germany or Europe, we often use also the air equivalence ratio, which is just 1 over phi. So when we consider combustion kinetics, we have to consider chemical species, the type of reactions, elementary reaction steps. We have to develop mechanisms, mechanism, detailed reaction models. We have to consider ignition and peroxychemistry, and at the end also we will discuss reactors and diagnostics to investigate chemistry on the molecular level. So this is very, very important, of course, if you want to consider efficiency. So for example, peroxychemistry is very important, especially at low temperatures. So you can have unwanted ignition phenomena and so on. So we will discuss the fundamentals of elementary reactions, and we will discuss experimental methods, maybe mainly in another part of this lecture. So chemistry. So of course we have our atoms, hydrogen, oxygen, carbon, nitrogen here. We have our molecules, methane, oxygen, carbon dioxide, water, and the reactions we consider are taking place using radicals. So we have the OH radical, the methyl radical, HO2. So we have different levels here, and at the end, if we consider, for example, pollutants, we also have a lot of aromatics, so classical benzol, toluol here, or benzene, toluene, and these form higher hydrocarbons, so polycyclic aromatic hydrocarbons, which then at the end can form soot. And here, for example, then we have very, very specific molecules, propagyl radical, propene-alene isomerization, which is important for soot formation. So if we have to consider this, we have to go very deep into the chemistry to understand this properly. And so the molecular structure of our combustibles is of course important concerning the combustion properties we have. So when we look here at these different molecules, so we have cyclic hydrocarbons. So benzene, when it burns, forms a lot of soot, and THF has nearly no soot, and here this explosive at the end, RDX, has no CC bonds, and therefore it does not form any soot at all. And on the other hand, we see this knock tendency, so unwanted explosions, pre-ignition in our combustion engines. So we have these molecules which with a complex structure which is very stable. So the tendency of knocking is very low here, and then we have this heptane here which easily tend to knock. So when we then look at the details, okay, we have seen the one equation already, CH4 plus O2 gives carbon dioxide and water. This is not the level where combustion takes place. So that's a global reaction. So we have our fuel plus an oxidizer giving the products. But the real life happens on this level, on the level of the elementary reactions. So we have methane, which at the end gives carbon dioxide. but it depends, for example, on the stoichiometry. If you have a fuel-rich mixture, then it takes more in this way, reaction pathway. Or we have a lean mixture, it can take more this way. So we have a lot of elementary reactions here, and we have a lot of intermediate species to consider. So for methane, classical reaction mechanism has around 50 species and then 150, 200 elementary reactions to describe this system properly. And larger hydrocarbons can have thousands of elementary reactions and hundreds of species which we have to consider. So, which is then quite large. And then, of course, if you consider, for example, numerical simulations, very expensive, because for each species, normally we have to solve one differential equation. So this overall global reaction here, H2 plus O2 gives water, can also be divided into a lot of elementary reactions. So we have an initiation of our reaction. So here that's the formation of hydrogen radicals. Then we have a chain propagation. So one molecule reacts with a radical and gives another molecule and another radical. H2 plus OH gives water and H, for example. We can have a chain branching, so H plus O2 gives H plus OH, so one radical on the left-hand side and two radicals on the right-hand side, which accelerates our combustion process. But we also can have termination, so H plus O2 gives HO2, and so on. So we have a lot of different reactions to consider, and finally we also have to consider wall reactions depending on our system. So the rate of an elementary reaction is determined by the concentrations and the rate coefficients. And the rate coefficient K depends on temperature mainly, but also it can depend on the pressure. So the example here, so the elementary reaction is H plus O2 giving OH plus O. So the temporal change of the concentration of the hydrogen atom is equal to K times concentration of hydrogen times concentration of O2, and so minus dH over dt is equal dOH over dt, and the formation of O2 of O has the same rate than the formation of OH. And these are normally following in the classical Arrhenius form, so K is equal in pre-exponential factor times temperature times the exponential factor where we have the activation energy EA over gas constant and temperature. And often this temperature here, or this temperature coefficient, has also a temperature exponent. So it's not always equal 1 or 0, it depends. So, and the focus of this lecture part is here how we can determine experimentally and theoretically the elementary reaction at the end to form or to yield a proper reaction mechanism. So it's very important is to consider the order of reactions. So if it's, for example, of the order 1, first order, so then we have this logarithmic equation. So the concentration of A at time t over the concentration of A at the beginning, the logarithmic of this ratio is minus k times t minus t0. So we have a linear relation here. So a linear decay when we look at this logarithmic term here. And for second order, it looks different, of course. So we get different results depending on the order of our equation we have to consider. So we have a lot of different type of reactions. So isomerization reactions, parallel reactions, consequent reactions, chain reactions. And this has to be considered if we want to develop a proper reaction mechanism. So one example here, isomerization reaction. So that means the molecule has the same chemical composition, but it changes its structure here, butane and isobutane. So this is very important. So because the different molecules we here then consider, then of course reacts very different in further subsequent reactions. So we have parallel reactions. So A can either form the molecule B or the molecule C here in this example. So the temporal change of concentration of A is equal K1, so reaction 1, A to B, times concentration A plus K2 times concentration A, and the overall reaction rate is K1 plus K2. So we see it here. So we have this exponential decay of A, and then the formation of B and C depending on the values of K1 and K2. And we can use then this simple equation system to calculate the consumption of A as a function of time and the formation of B and C as a function of time. So it's quite simple here to have a look at this system. We can have reversible and or opposed reactions, which then of course looks much more complex, but these are just two elementary reactions. For example, here in this example, the forward and the backward reaction we have to consider. We can have consequent reactions, so A gives B gives C. So, and again, here we can use a quite simple equation system to calculate the temporal evolution of all the species here. This is very important because in some cases the consequent consequent reaction B to C is much faster than A to B, and then often we can neglect this slower reaction, or the faster reaction, because only the slower reaction is dependent on important here. So chain reactions can be observed in a lot of applications, so populations of bacteria, nuclear reactors, and of course chemical reactions. And the idea is, so we have an temporal change of a quantity, and this depends on the reaction rate and the amount of the quantity, and it can either be smaller one, larger, smaller zero, larger zero, or equal zero. And then of course either we have a decay, if it's smaller zero we have a growth, or it's stable. And we have several types of chain reactions, which I already have explained on some of the previous slides. So temperature and pressure dependence of our reaction rate. So we have this Arrhenius type. So this Arrhenius equation, K is equal pre-exponential factor, and then activation energy over gas constant times temperature. And when we look, for example, at this decomposition of H2O2, we see the temperature, the reaction rate depends more or less linear here from 1 over T. So classical Arrhenius equation. We also can have a pressure dependency. So the reaction rate changes with pressure. We have more or less two different reaction rates to consider. One is here the infinity value at high pressures, where we have more or less constant value, and at lower pressure this K changes with a specific function depending on our reaction. So we have discussed a lot of terms now. We have discussed elementary reactions and the dependency of these elementary reactions. So the question is now, how can we use this? Why we need it? And so the idea is, of course, to couple all these differential equations to form a chemical mechanism to describe the combustion of hydrogen or of propane or of diesel or jet A or whatever, considering as many chemical steps necessary to describe our system properly, but of course to describe it in a way as efficient as possible. So neglect reactions which are not of importance and focus on the reactions which are really, really important. So we have to combine all the elementary reactions we have to describe our combustion systems. Here in this example we have 5 different reactions, and at the end we have to couple all the rates together when we want to look at the formation of all the species. So H atom we have to consider here, 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 and here, and here. So it's either used or it's formed in the reactions we have. So we have to know the reaction rate of all the reactions we have to consider here, and we have to know the concentrations of all the molecules and atoms we consider here. So at the end, the temporal change of the concentration of H in this example depends on all 5 reactions here, and we have to know all these data. So we have the same here now as an classical equation. So we have to consider elementary reactions. The number is here R, and we have to consider S species. So at the end we will sum up over all the equations the change of the amount or of any molecule. So at the end we yield a description like this one here. So the temporal change of the concentration of each molecule is then just described as the sum of all the reactions this molecule is involved. So this is we have to consider. So this is the global expression, and here this is the example for this specific case. So of course, if you have hundreds of reactions, then you have to, of course, consider much more details here. So a reaction mechanism is a coupled set of differential equations for all species involved in the reaction steps. So it is a large database. We have to know the thermodynamic properties, so heat capacity, enthalpy, and entropy mainly of all the species, to calculate the reaction rates here. And then we have to of course to know the reaction rate parameters, so the pre-exponential factor, the exponential term here, and the activation energy. And I've said it before, the size of the mechanism we use strongly depends on the molecules we consider. So H2 can have a quite small mechanism. In this example here, 7 species and 25 elementary reactions. And in case of this cetane mechanism, as a diesel surrogate, we have 1,200 species and 7,000 elementary reactions to consider. So how do we develop such a mechanism? So we can use theoretical concepts. So there are existing reaction mechanism generators. So where we more or less, or simply speaking, we say, okay, we want to describe the combustion, for example, of methane with oxygen. And this mechanism generator then sums up all possible molecules which may be involved in this reaction and all possible reactions which can take place. So it gives you hundreds of species, thousands of reactions. And the idea is then, of course, therefore it's a generator to filter this big list we have and to get a smaller proper reaction mechanism at the end. We can use the so-called master equation to describe our system, a more classical concept, but based on quantum mechanical calculations. This is maybe the future concept. So we describe the different states of our system in all details using quantum theoretical calculations and get then the reaction rates of all the reactions we have to consider. So in the future, with enough computer power, maybe no one is bothering about any mechanism reduction and so on, because then the computers are fast enough to handle even very big mechanisms. Then of course the traditional setup is CH4 plus O2 gives CO2 plus H2O. So what are the reactions I assume? So what radical reactions I may have to consider? So someone can write down this by hand. So an approach like this RMG, but the traditional approach. Or we can of course then look into the literature and then see for different sub-mechanisms, maybe different reactions. So for linear combustion, we may find different reaction rates compared to rich combustions, and so on. And finally, of course, we need experiments to look into at least some of our reactions into detail to determine the reaction rates. So here an example, the thermal NOx formation, or so-called Seldovik mechanism. N2 plus O gives NO, so nitrogen monoxide, and we also have then N plus O2 again yielding NO. So we get here 3 differential equations to describe the formation of NO and the decay of N, decay and formation of N, and the usage of O2 here. So this is a very, very simple sub-mechanism then to describe the NOx formation in combustion processes. Another example is the typical beta decomposition of hydrocarbons. So here we have our propane molecule, which is attacked by an OH radical. This takes one H atom to form water, and then of course we have this radical here, this N-propyl radical, which then normally decomposes here at the beta position, and we get ethene C2H4, which then may form acetylene at the end, C2H2, a classical soot precursor, and we have this methyl radical, which then gives formaldehyde as a stable molecule on this side. Can be very complex. So we have here, for example, the reaction of methyl radical plus O2, which gives this intermediate molecule here, and this intermediate molecule can either decompose in this way or this way, or form another form of this molecule here, and you see we have different energy levels when we look at this reaction coordinate, and of course all reactions can take place, and the the science is here now to consider which are important for my specific combustion process. Is only this way here to formaldehyde plus OH of importance? Or do I have to consider also the other reactions I'm describing here? So I think, Professor Sahoo, I already have used 1 hour now, right?
Sorry?
I'm talking now for 1 hour?
Yeah, it is not that mandatory, but
No, so maybe we can have a break here.
yeah, break here, lunch break, then after lunch you can start, continue from here.
So this is then part 5. Okay, we can change it?
Yeah.
Yeah,
you can
okay.
change it.
Yeah, okay. Okay. So we have now a lunch break.
Yeah.
And then
already 1 o'clock, close to 1. You have not started. Another 15 minutes.
okay, okay. Okay, that's a different time. Okay.
If you want to continue, you can continue. Otherwise, you can take a break. After lunch, you will continue. We have enough time. I think
Okay,
that
then.
is better.
Then we will take a break now and we'll continue after lunch. Okay, thank you.
After 2:30.
Okay.
that is properties of this gas mixture. So, why we require this kind of study while doing this combustion analysis? Because any kind of chemical reaction you look at, starting we have a fuel and air, they are to be mixed. Now, when we have fuel and air mixture, at the end of the reactions, we used to have combustion products. So, how do you quantify the various concepts, like how much energy is dumped into the system and how much things you are going to get out, whether this reaction is proceeding in a proper direction or not, and if it is proceeding in certain direction, through this process we need to define various combustion parameters, which I will be dealing with separately in subsequent lectures. But here the knowledge of thermodynamics comes into picture because it gives the direction of any chemical reaction, how it proceeds, first thing. Second thing, if it is a mixture, how do you calculate the properties? Because normally in thermodynamics, when you solve classical problems, either it is a gas, mostly it is a gas, single phase systems, but whereas in a mixture is essentially defined by variety of ways. It can be solid, liquid, it can be solid, liquid, solid, gas, various possible combination is there, maybe solid and vapor, many possible combination is there. But in reality you have to say that which type of mixture you are dealing with. So, thermodynamically we deal with various substances as three phase, solid, liquid and vapor, and these substances can be of any matter, which there are some definitions in which it qualifies as a pure substance. Now, out of those models, which we are going to fit it for analysis of a combustion systems. So, background thermodynamics actually tells you lot of analytical modelings and how to proceed further. That is the essential feature. So, classical thermodynamics necessity is required to define a gas mixture, but actually if you look at combustion systems, it is fuel. Fuel may be in liquid form, but when it actually interacts with oxygen, air, it gets vaporized because it is a compressed air, high temperature environment. So, actually it is vaporized. So, how to deal with these things? When it vapor, it all of a sudden liquid does not go to vapor. There are some way that there is a phase change process that is involved. So, for that how to quantify all these things? Only thermodynamic viewpoint, we have to define those parameters. So, that is the role of gas mixture in the analysis of analysis of combustion systems. So, on this heading we will talk about basic philosophies, that what is the pure substance and what are the different phases. Then if for every substance, when it exists at certain phase, what is the kind of equation state which you can define. Now, coming back to gas phase only, because gases are only compressibles. So, for that handling gases, we have like ideal gas model, real gas model, and to qualify this real gas model, we have to talk about something on compressibility chart, because that says that whether your ideal gas modeling is valid or not, or under the working domain of your properties, pressure, temperature and volume, whether that gas behaves an ideal gas or we have to go for real gas modeling. If it is a real gas modeling, then what is the change in the equations? So that is one aspect. Other aspect, it gives the impression of about how do you find out basic relations for gas mixtures, because in our beginning or first phase of discussions, when you deal with thermodynamic systems, we talk based on the different laws, we talk the parameters of like pressure, temperature, volume, enthalpy, internal energy, entropy, all these things needs to be quantified, and that is for a single system, a single phase. But when the gases are mixed, how do you evaluate that mixture properties? So what are the different laws, rules that allows you? So that is what we call as a basic relations for gas mixture. Now coming back to basic relations, many a times when you talk about basic relations, we really do not have a various parameters, we do not aware of certain parameters for variety of substances. But what we can do that is that had that substance behaves as an ideal gas, what would have been this, what would have been its corresponding parameters. So ideal gas mixture modeling is also required to give an initial estimate. Then if you want to improve your accuracy, keep working on introduce various models, and when you introduce those models, you try to see that how much deviates, whether ideal gas model is okay for me. If it is okay, then better go ahead with that. If not, you go for a real gas model. Why this is required? Because such kind of tricky modeling you have to introduce when you actually do the modeling with computational studies, because many times real gas modeling may be a complicated affair. So ideal gas modeling will be a better estimate. Then we will talk about something on mechanism, what are the different mechanisms in which we can actually model the mixture and then find out its properties. So this is the overall picture, and all these things are required for our analysis. Now while dealing with this mixing analysis, one fundamental assumption we make is that whatever contents or constituents of the mixture we prepare, at the end of the mixing process, we also always find the same kind of substances, like we mix salt and water. So at the end of the day, we will have the salty water. So here salt remains there, water also remains there, but we get a preparation of mixture, but which is not true when you do combustion reaction, because the mixture has lost its parent identity. So that is only fundamental difference, but this will give you some kind of, what I am saying, entire analysis will give you some kind of thermodynamic estimates. So this is the how you are going to link this exercise with our combustion study. Now I will just briefly talk about what is pure substance. There is nothing new in it because it is available in the textbooks. Pure substance qualifies with the fact that entire structure, the quantity of matter is homogeneous throughout. So if I say air, if I say nitrogen, it is either in molecular form, its structure is homogeneous throughout. If it is salt, it is homogeneous throughout, even though salt remains as it is in an entity. But again, air also qualifies as a pure substance, even though it has a lot of things like nitrogen, oxygen and everything, but they are of fixed quantity. percentage wise they are of fixed quantity. So, such way that pure substance, air also qualifies to be a pure substance, which the main fundamental point is that it is homogeneous throughout in terms of chemical composition and physical structure. Now, when it is homogeneous throughout and it is a pure substance, then we define its phase. It exists either in solid, liquid and gas phase, and for this kind of things we follow a rule which is called as state principle, means to define the pure substance at certain situations we really have to talk about its composition and the state of the system at that particular things, at that particular parameters of properties, and when you say it is a pure substance, we need normally represent them in the graphically through this pressure, volume, temperature relations, and there we talk about different phases. So, what are they? So, it is in a PVT surface there are three basic parameters, pressure, specific volume and temperatures, although there are other parameters, but all others are derived parameters. Let us say enthalpy, it is a derived parameter even though it is a property. Entropy, it is a derived parameter although it is a property, but basic properties which are like this: pressure, specific volume or density, then temperatures. So, we put them in a PVT surface for the substance. Some of the substance they contract during freezing and some of the substance they expand. So, classical diagram that includes in our viewpoint of analysis is pressure temperature diagram. This pressure temperature diagram, because if you look at this, out of these three properties we only talk about two independent properties. By two independent properties I mean we cannot take volume, specific volume and density as one parameter, because they are interrelated. So, either it has to be temperature volume or pressure volume, or it can be temperature density, pressure density, other could be pressure temperature. These are three possibilities we can bring out. Now, while dealing with this, one thing that distinguishes different phase of the substance is that it is a pressure temperature diagram, and this diagram we call this as a phase diagram. So, phase diagram talks about three different phases of a pure substance, and here you look at two important coordinates. One is this point what is called as a triple point, other is this point which is critical point. So, what the diagram talks about, in one axis temperature varies, other axis pressure varies. So, at we can say very low pressure, low temperature, we are in this zone, and independently we can vary temperature as well as pressure, and slowly the substance tries to change its phase. So, with variation of properties we can draw them, and there by doing so we will try to see whether the change of phase occurs or not. So, if it occurs, what are the different phases? So, you define this as one as solid region, other is liquid region and other is vapor region, and beyond this we can call this as a gaseous region. So, there are some criteria. How do you talk about this? First thing is that when you one point you say triple point, there typically for every substance this temperature exists. This is very low pressure and low temperature zone, and at this point all three phases coexist. Now, side by side side by side, if you can increase pressure and temperature as well. So then while doing so, we can try to see whether there is a change of phase with our changes of pressure and temperatures. So then we can see distinguishly mark the solid and liquid regions. We can also mark vapor and liquid and vapor regions. So that way this process keeps on going till we reach this critical point. So at this critical point, it is something like that we are talking about liquid and vapor only. At this we do not talk about the solid region, it is only liquid and vapor region. And if you still go further, we will have superheated regions. This is typically what we see in the steam table or water diagram. So these are superheated regions. Now this is one aspect when you say change of phase. Now in this another point that needs to be, many a times we say that vapor and gas, are they same? So vapor could be a superheated vapor, it could be a saturated vapor, it could be a solid liquid things which you can find out in temperature volume or pressure volume diagram. But to make some distinctions, what we can find out that vapor and gas, they are not really same, because controlling parameters are both pressure and temperatures. So, but at certain conditions, the vapor behaves as gaseous, behaves in because the equation of state is different, because when you say gas regions, ideal gas, we are using one model PV is equal to RT something, but that works for if that works for vapor, which means vapor and gas conditions, they are more or less same. So basically when I deal with compressibility chart, I will talk about what is the distinction between gas and vapor. Then some parameters we define, like we have sublimations, when there is a change of phase from solid to vapor directly. Then we have solid to liquid, we talk about melting. When you talk about liquid to vapor, it is either vaporization or condensation. Things can move in forward direction or reverse directions. So that way we define various parameters, and some point of time we talk about saturation. Saturation means if the state point lies on this line, it is a saturation line. So more details we talk, I think, in the steam tables in our earlier classical thermodynamics course, but that has no relevance for our understanding, because we are mostly dealing with the gaseous regions or high temperature or pressure. So this is again to give some numbers. You can set, when you talk about triple point for water, you can see how much very low pressure and temperature is 273 or 0 degree, it's this much this Kelvin, and for water is this number, and we have for every substance we have parameter like critical pressure, critical specific volume, all these things. So here this is another way of interpreting the phase, interpreting the pure substance analysis, which typically we use them for the change of phase from liquid to vapor in a pressure volume and pressure specific volume diagram, PV diagram, where some substances that expands during freezing. Freezing means actually this line, this solid line, solid and liquid regions. Again we have same thing, here it is represented in another form, where we are introducing temperature specific volume diagram for similar type of substances. Okay. Now understanding this, so this is all about the things that we talk about in various thermodynamic diagrams. Now for all these things, there are two ways to look at how do you analyze quantitatively. Quantitatively means you have to frame some equations and that equation is valid for some domain, some working range, all these things. So, mathematically it qualifies in the area that representation we do in terms of equations. Okay. So, there are equations, what we say that thermodynamically we say there are Maxwell's relations, there are all partial derivative equations. Those equations will give you the mathematical feel about this course, about this property of a substance. Then we have this tabular representations, like we have stream tables for variety of substances which you commonly encounter at UG level of this thermodynamics course, steam table, refrigerant tables, all these things. Then on a PVT surface there are specific diagrams, what we have a molar diagram which is enthalpy entropy diagrams. We have this compressibility chart that is mainly for gaseous substances, whether you have real gas or ideal gas. Then we make analytical formulation by knowing one properties. It gives a feeling that equations that we can also find the other properties. Now, in a now our with this background, our main philosophy that we are not actually dealing solid liquid, although fuel exists in liquid form, but when it or it can have a solid fuel as well, solid liquid these fuels as well, but still when it goes for combustion mode with reaction of air, it really we make it really in vapor form, because we cannot store energy at gaseous level in gaseous phase, because your energy density will require huge energy density because you large area. So, it is easiest to store the fuel in the liquid form or solid form. So, conventionally when you see for high end combustions, I mean high end high speed combustions, they use solid propellants, because that is easy to ignite, that is easy to because entire energy we are condensing in some form, because solid occupies the out of this energy density in higher in the solids. But same energy if you want to have it in a gas phase, you require large storage. So, that is the reason the analysis whatever way of energy storing in the fuel, but actually when it goes to combustion mode it is a gas phase. So, that way we have to model either ideal gas or real gas. So, here there is a catch that how you under what circumstances how the any kind of vapor or gas behaves. So, there is a mathematical insight to it, is that what it says is that if you look at gas, it is a well behaved thermodynamic substances, and if you want to calculate for every gas, any gas you choose, you calculate the actual pressure at which it exists, which is P, and for that gas you find the corresponding triple pressure value PTP. So, pressure of the gas to the approaches to a value which is independent of the nature of the gas, which means if you take CO2, find its CO2 at let us say 1 atmosphere, and find the triple point pressure for CO2, you will have a ratio. If you take nitrogen at 1 atmosphere, find its triple point value, corresponding triple point value. They are independent on the nature of the gas. That means, we do not talk about nitrogen or oxygen with or any gas, you take about the ratio, as when this approaches to 0. So, that is the criteria, and this makes us to form a mathematical model in such a way that how a ideal gas equation gets evolved. So, for any gas, if you take pressure and corresponding value V bar is molar specific volume, and its value is some for a limiting case when P tends to 0, it approaches to a value which is a function of temperature and independent on the nature of the gas. If you do some calculations considering the fact that you choose the Kelvin scale and find this ratio, ultimately it boils down to a fact that limiting value of this becomes R bar by T, or we simply write this limiting value becomes, this R bar is nothing but a universal gas constant, and where T has to be represented in Kelvin, and all the numbers what you see here, we talk about number of moles. Okay. So, this is the evolution of ideal gas equation, how it gets evolved, and ultimately we really do not bother when you actually solve the problems, we really do not bother how that equation comes out, because it is simply one equation. But this is the evolution how that ideal gas equation gets framed and what is the logic behind framing that equations. Another way of looking at thing is that there are, over the years there are many formulations. Before you come back to ideal gas equation, there are people try to have many formulations, because that point of time only mathematics was there, but how to make relations among the parameters, that was not known. So, there are several ways people try to attempt for variety range of pressures, like one case they talk about 0 to 40 atmosphere. Likewise, some people talk about this kind of equation of states. This is nothing but something like mathematically these equations do exist, we can frame, but reality how do you correlate that? So, people try to frame in this manner. There are other equations some people try to frame in this manner. So, they say this is my equation of state, other groups say this is the another kind of equation of state. So, there are lot of equation state that evolves, but ultimately and through this process people try to have a common understanding that how to represent them in a graphically for in a more convenient manner, and when they do it, those frame this equation of state, they try to represent in a graphical manner with variety of plots. One such plot is pressure, one axis, and other is PV bar by T. What it says is that what I mentioned this equation earlier, that for at given temperatures T1, T2, T3, T4, you find out this P as a function of this. You draw these curves at different temperatures, and when actually you extrapolate or maybe extrapolate, it boils down to one particular point for irrespective of what temperature you are. So, we call this as a R bar, and that they call it as a universal gas constant at later point of time. But still then that does not solve the purpose, because these two have certain units. Some people interpret pressure in atmosphere, some people interpret in the different form, and they will that also has different properties. So, then further simplification was done, where the compressibility chart was evolved with the fact that how do you bring down, irrespective of what type of gas you are, how to bring out down to a common platform. So, for that things we defined some of the non-dimensional parameters. One such thing is a reduced pressure, other is reduced temperatures. So, for reduced pressure and temperature, how do you define that? You take any gas which exists at certain pressure and temperature, and for that gas you calculate its PC, critical pressure. So, you can find out for CO2, N2, all kinds of gases. Similarly, critical temperatures. So, once you know this, these parameters are non-dimensionalized, and of course, specific volume can be calculated from two ways, like one this, or we can also find out from these two parameters. So that way the earlier analysis gets evolved in a more better manner. So, what we are trying to plot here is two parameters, because the two independent parameters are this PR and TR. So, one axis we have kept reduced pressure, and this is and then instead of finding out PV by T, they have introduced the parameter either R bar or R, any one you take and you represent them. So, this they call it as a compressibility factor Z. So, that way both axes are non-dimensionalized. Through this non-dimensional form, if you look closely, one interesting result was developed in a sense that other axis, this one part things, other thing that you have is that they have to be plotted at different TRs, because pressure and temperature, this thing. Interesting fact is that you do carry out the study. Let us say you take one particular value, let us say TR is 1, we are trying to plot PR versus Z. Significantly, we found that irrespective of type of gas or substance used, like this is they follow a typical pattern, means all the gases for at 1 TR and 1.5 things, all these numbers boil down to a single point irrespective of what substance you are using, and they follow a typical trend at different TR. And this is true for all kinds of pure substance analysis. But what the message it talks about is that there are some regions, we have to see that what is the lower limit of Z, what is the upper limit of Z. So, maximum possible value of Z can be of 1 and minimum possible in this graph it is 0.2. That means, when we are looking this point value at this point, this is a zone where we are looking at lower pressure, and of course, TR is lower, and of course, the range of TR that come across, it is only between 1 to 2, because that is because it is a non-dimensional T by TC. So, its value ranges from this. So, all our data gets inserted into some zone of TR1 to 2. So, TR1 means it is a lower region, TR2 means we are higher regions. So, when we are looking at that particular substance in this zone, this is something like lower TR and lower pressure, there is a effect of compressibility. As you go this side, keeping this axis, still compressibility effect is there, this side. But compressibility effect drops as you go higher TR, like if you take this particular line. So, ratio hardly varies from maybe 0.98 to 1. So, this is the zone where we say that compressibility effect gets nullified with this our analysis, and that way we say that that particular, and this is also true for most of the cases, almost most of the pure substance. So, that way it qualifies to a fact that this kind of analysis can be treated in a different manner. So, the evolution of equation of state comes into picture, and when actually we are looking at compressibility effect, So, whatever analysis, standard analysis you do, typically normally we call it as a real gas model. So, those models gets further needs separate attention, and that way this ideal gas model was framed. Now, when you say ideal gas model, when you are looking at this zone, we frame some simple equations like ideal gas equations, and then their molar analysis, all these things that comes and equation. So in the limiting case, what it says that this compressibility Z tends to 1, which means PV by RT tends to 1. Such things we can treat in a different way. So, we call this as a ideal gas model. So, this is on one, and this equation is true for all kinds of cases where ideal, we use it, we call this as ideal gas equation of state. Now, coming back, in some cases the ideal gas doesn't fit to our expectations. So, some cases we call them as a real gas model. So, all these one typical equations of real gas model, which we all know is a van der Waals equation of state, and this real gas equation makes some assumptions that there are two fundamental concepts involved, where while framing this equation. So, actually it is PV is equal to RT, but B is interpreted in a different manner by considering the fact that gas molecules occupy more volumes with respect to ideal gas molecules. Means in the ideal gas, size of the molecules is neglected, although because they occupy a certain volume in this in the container where it is kept. Other thing is that when it is kept in a container, we normally do not take into account the effect of attractive forces among the molecules, and they exert some pressure on the walls of the container. So, considering this, we say that the actual volume is lesser than the size of the container, and the pressure is pressure which is supposed to be there, it gives an additional value, because we are talking about the wall effect of calculating the pressure. So, that way for every gas we find some typical constants A and B through this van der Waals equations, and most of the cases this equation is true and valid for most of the cases. So, that is what this equation takes a prominent attraction for modeling a real gas. So, these are some standard calculations through this van der Waals equation of model. One can actually calculate the critical pressure, temperatures value, and also you can calculate the compressibility factor, so many things. That is what it has some certain advantage, that when you use analytical form of equation in a van der Waals model, we can really frame your coding or anything through certain equations without entering into the data book. So, these things I already explained. Then we will move on to this gas mixture. Okay. So, after quantifying this ideal gas and real gas, we will now move up to gas mixture. So, when you define a mixture, I mentioned that one mixture can be and when you talk about specifically for gas mixture, the possibility that we can mix nitrogen, oxygen. Air is a typical mixture, but it behaves as an ideal gas. We can mix nitrogen and oxygen, we can nitrogen, helium, so many possible combination can have. So, when you mix, it is in our control that we can mix in its molar form or mass form. Okay. Mass form and molar form we can mix, as long as we are doing the mixing analysis, mass form is still okay. but when you do combustion modeling, mass form is not okay, because it's not possible, because end of the day your products are vanished, I mean the reactants have vanished, so the products have formed. So it is basically the molar analysis takes the lead. So while showing here, we define them in certain parameters. When you mix them, when you prepare the mixture, we talk about mole fractions, number of moles, and there are, and here this mole fraction is yi. For every constituent you have to give its mole fraction value, and the standard relation says that they boils down to a fixed number of moles can be added. This is one equation what you see. Other kind of standard rules when you prepare this mixture is that when you prepare the mixture, when you actually assume that you are not talking about a real gas effect, and if there is a compressibility factor entering into our analysis. So the mixing laws are defined for in two ways. One is, we call this as a case rule, other is the additive rules. So parameters of interest, we have pressure, temperature, volume. So individual entities will have different values of pressures. Like we are mixing three substances, they will have its own pressure, own critical value of pressure, own critical value of temperature, their own known properties, and when they mix, will have a mixer properties. So if you are having three substances, every three substances have their own properties, and once they mix, they behave in another properties. So then in that case, how do you calculate the mixer pressure, mixer temperature, all these things? So there possibly one way is that when you talk about the pressure, this case rule tells that one can write these things. The P1, P2, P3, they are individual pressures, and that individual pressures are judged at their respective temperatures. Now when they are mixed together, mixer has certain pressure and temperature and volume. So mixer temperature is P, T, V. Now total pressure of the mixer is evaluated based on their individual pressure, but it is corresponding to this mixer temperature and volume. Similarly for volume, when you calculate, it is with respect to mixer temperature and pressure. That is one thing. Second thing, whether that each independent entities, whether it behaves, whether it has a compressibility effect or not, that thing we can be just through parameter of this compressibility factor. And for each individual constituents, we can have its individual pressure of, let us say component I, it has Pi value, but when this component becomes a mixer, the mixer will have a different properties, which is P. So it is at component level, it is at mixing level. This is how it is defined. This is one way which we call as case rule, and then there are additive rules also. Why means these things we can add it. So once we have this, this is about pressure, temperature and volume, all these things basic parameters. Then what are the derived parameters? Derived parameters could be your internal energy, entropy, any other thermodynamic properties, entropy, enthalpy, any extensive properties which can be calculated. So for a single phase, single component systems, normally we use this. So this is again same to what a single phase analysis. Now for a multi-component systems, what changes here, because temperature and pressure remains as it is, their respective number of moles becomes different. So when these for a single phase and multi-component systems, you have to know all these molar values, number of moles. Then from this equation, if you want to calculate the molar property value of, then it has to be if you define this particular xi parameters, corresponding molar value one can find out in this manner, because each one will have a different number of moles, that is what it is Ni, and this is actually its a molar value, and this is mass specific definition, it is molar specific definition. So, that way one can find out variety of thermodynamic parameters. In particular in thermodynamic term we call this as enthalpy, its mass specific value, molar specific value, and also we have entropy, internal energy, all these functions are there. So, all these functions gives true value when they are treated at an individual level. But in combustion studies, we try to introduce additional terms. One is like a Gibbs function and other is Helmholtz function. And this for example, when you talk about open system, we talk about enthalpy. When you talk about closed systems, we talk about internal energy. But those two terms is not sufficient. These two terms are sufficient when you are simply dealing with a single phase air, carbon dioxide, nitrogen as a single case. And when you have a mixture, initial mixture, and when it lost its identity after the mixture, then those numbers really do not play a key role. So, that way some other terms were defined mainly for combustion studies. Typically when you deal with the chemical thermodynamics, if you look at UG level, we have thermodynamics is being taught in the mechanical engineering, energy, also you talk in the chemical things, but they are more specific about chemical thermodynamics, where they study more on this Gibbs function, Helmholtz functions, and those are nothing but combination of enthalpy, temperature, entropy, and like that. So, that way I can emphasize that these terms are more appropriate when you study these reactions. So, having said all these things, if all these K rules, additive rules are governed when you talk about the effect of compressibility, and when you do not talk about effect of compressibility, that mixing system itself, if you can say, behave an ideal gas, then the analysis becomes further simplified, and we call this as the ideal gas mixture. When I say ideal gas mixture, simple equations PV is equal to RT holds good, and through that thing we keep on doing this analysis. So, that way you can get a easy estimate without involving complexity into the systems. So, there are processes that we can, through this ideal gas analysis also, one can think either in the form of mass specific analysis or mole specific analysis. So, that way we call it as a, when you talk in terms of mass fraction, experimentally we find out which is called as galvanometric analysis. When you say mole specific or mole fraction, we used to call this as a volumetric analysis. So, that way for combustion studies we will be more focused on the mole specific analysis equations. So, if you do mole specific analysis, what the equations whatever you have studied so far, it becomes a simple analysis which says that there are n number of gases which gets mixed, N1, N2, N3 gives n moles of mixture, and the total fraction we can use this equation, and from this we can define mass fraction, we can calculate the mole fractions, and their summation happens to be 1 because this equation are also true, and from there we can if there are n number of mixtures, then we can also find out a molecular weight of the mixture. Molecular weight of nitrogen, molecular weight of carbon dioxide, they mix together, but ultimately what happens to the molecular weight of mixture. So, that way we define molecular weight of mixture, then mass, all these things we can calculate. So, simple case study, if you look at, air contains 78% of this, 21% of oxygen, which is major constituents, and from this we, in a simple analysis of this mass fraction, we can calculate the effective molecular weight of air, which is this. So, this number we keep on using, but how this numbers gets evolved because of this ideal gas equation of state. Now, this is something similar to this. Typically, thermodynamically we use this ideal gas equation in this manner, and we have this partial pressure. Then once you have this, we can, if it is a mixture, we can find out its component level pressure, and also we call this as a total pressure. But here I will try to emphasize that we talk about K's rule when you talk about pressure, but that K's rules effectively becomes a Dalton model when the system behaves as an ideal gas. So, typically we know this Dalton law, which talks about summation of each individual pressure becomes the total pressure. This is actually Dalton's law, which comes from the main real gas model analysis. So, from this we have we find all other parameters in terms of volume, mole fraction, and like that. So, when you have all these things, pressure, temperature, specific volume, we have at individual at individual level and mixing level. Then combinedly, when they are kept it, what are the other parameters? Other parameters that we interested is the internal energy of the mixture. We are interested in the enthalpy of the mixture, and then we are also interested in the entropy of the mixture. So, they have to be also, we can easily model once you know their individual mole fractions. And these summation equations becomes very vital to effectively model a fuel air mixture. We have a fuel, we have a air, and if they behave in an ideal gas mixture, and initially when you calculate its enthalpy, entropy, all these values, we can find out the respective constituents of fuel and respective and air as a whole, and we can find out these mixing properties. And fuel may have some additives, that part also takes a part of mixture. So, through this one can effectively find what is the initial state of the mixture, and correspondingly when they are mixed, we also we need information about their specific heat of the mixture at constant volume and constant pressure. So, this is about this ideal gas modeling. Now, when this mixture gets prepared, there are possibilities that like you might have seen that in our IC engine analysis, when the charge enters into the cylinder, either it is fuel air mixture enters or air enters and air and enter, they come in a separate manner. So, when they enter and their things, when the how that mixing is prepared. So, the mixing preparation can be modeled like mixture. When mixture goes, we assume that when it enters, the energy what we say, whether it remains in an adiabatic manner or energy tries to dissipate through the cylinder wall, or if it is a flow systems like combustion chamber or boiler, maybe in a steam power plant where fuel comes and fuel and air comes in a different route, mixture is prepared, we treat it as open systems. So that way different parameters of mixture things that can happen, where with that gases which are initially at different temperatures, gases which are initially at different pressures, and the gases which are distinguishable from one another. So variety of ways where mixing can happen. And when we do this mixing, because mixing process thermodynamically is viewed as a irreversible process. Once mixing is done, it is very almost impossible to separate each of these things. So that way we are entering into irreversibility. Since we are entering into irreversibility, calculation of entropy is also required. So entropy analysis also vital. So through that way, that is the reason we call this as a mechanism of mixing process, whether it is done spontaneously or when it is not done spontaneously, then what you have to find out what are the difficult constituents levels of this mixing preparation. So through this the first thing is that when you talk about if you look at this particular figure, we have thermodynamic state 1 and there you have the thermodynamic state 2. So we have at state 1, for which we have this initial properties of the constituents. When the mixture is prepared, they have different state values, and when the mixture has state, not necessarily this U1 and U2 matches. So there could be possibility of change in the internal energy and enthalpy during this mixing process. So one way that we can effectively find out those things in a through our molar analysis, which is mass specific, which is mole specific, other is the mass specific analysis. So this is the way we say what happens in the change in the thermodynamic properties once the mixture is prepared. Then, and in these calculations we also have critical point or difficulty level in the entropy calculations, because entropy things we have to use these gas equations. So you have to see that what is that gas which is at initial state, and when it mixing is prepared, and what is the state when it is mixing. So through this we need to find out. But for this kind of analysis, we are going to introduce the concept of absolute entropy. So this absolute entropy I will come back when we go to combustion state, because the knowledge of absolute entropy is required because the parent constitutes lost its identity after the reaction. But in the normal mixing process, we know the in parameter state and out parameter state, so you can effectively calculate. So I will emphasize this point when you actually go for the combustion analysis, what is the role of absolute entropy and why that knowledge of absolute entropy is required, because in our conventional thermodynamic calculations we do not talk about this absolute entropy in a significant manner. So the thermodynamically this mixing can happen through a compression process. One you can say compression of an ideal gas mixture, which is typically happens in an engine cylinder. Fuel and air, when it are mixed together, it prepares these constituents. So when the mixture expands, compresses in a engine cylinder, this is a typical combustion systems in the IC engine, where we talk about fuel and air mixing at different position of the piston. Another is expansion. Such kind of expansion we see in the nozzles, And this typical analysis we come across either in gas turbine engines or rocket nozzles. So, there we treat this mixing, and when essentially in all those cases what happens, fuel and all those engines, they require thrust. We do not rely on power, they require thrust, and that thrust comes from the energy which is generated after the end of combustion, and that combustion products they try to expand through a nozzle. So, that nozzle, because when this pressure and temperature are so high, this gives an additional backward thrust for the body to move in the other directions. So, it is simply that Newton's third law, which thrust propels your body. So, this particular analysis we see that mixing analysis in a nozzle. So, modeling can be of ideal gas or also non-ideal gas. This is another case to case thing, that when you require the kind of mixing in an adiabatic manner. So, two fluids we are mixing together, initially they are separate and with a partition, and all of a sudden we try to mix them together, and when they are separate together they have their own identity, nitrogen or oxygen. When they have mixed, they will have a different identity, which means that initial conditions gets vanished when mixing is done. Now, if you use your similar thing, if I try to correlate with our combustion study, we have a fuel and air, and this you can think as a reactor, and initially you have fuel and air, they have their own identity. Now, you create a ignition so that they react to each other, initial state gets vanished, we are left with some combustion products. Okay. So, this is another way we can say, and in one cases why you say adiabatic mixing, if it is a reactor, we are not allowing this energy to go out. Okay. So, it is you can keep this as insulation, that after reaction this modeling help us what is the energy that we are going out, energy after the combustion, what is the kind of pressure and temperature level, maximum pressure and temperature levels we can expect. So, this helps us in designing this container wall thickness. This helps us the kind of temperature that this material is going to withstand. So, this is all about, although reality we try to expand to get this thrust and all, this is all about the design aspects of, if at all an explosion has to take place in a certain things, and we want this to be entire energy to be contained in the room. So, it will be properly isolated. So, kind of pressure and temperature level it talks about. So, this is required for just for modeling, and that modeling we can do at this individual level. So, this in the mixing of two streams, this is what we say, one way we say it is mixing within a closed systems. We can think of mixing which takes place, two streams they mix together and come as a common stream. So, that kind of analysis normally you do in open system analysis for gas turbine engines, where fuel and air comes as a different streams, but they while reacting they behave as a common stream. This is all about which I wanted to say about this mixer. Now, there are some kind of problem based on these lectures that we can try to see if time permits. So, all these things will be given to you, and you can work out and let us know these things, your output of this. So, this is all about my presentation as on today, and if you have any kind of suggestions or queries, one can ask, or you can take a break then come back. Okay. Is it okay, or you will want to continue and then finish? Okay. What do you suggest? Break. ठीक. Break के बाद मिलते हैं, because we need to sit for another half an hour, at least another 40 minutes at least. So let us have a break. No. After this, how much time break? 10 minutes? 20 minutes? 30 minutes break? 30 minutes is too much. You take about 15-20 minutes, then come back, because we will have because we will have some interaction session, and I expect that this interaction session you all of you should attend, because it is now your time to talk something about yourself, not to me, because I know all of you, at least to him. And while coming for this interaction, please make sure that you have to introduce about yourself, and mainly you have to talk about what kind of projects you are involved, and in master level, PhD level, all these things. Okay. So be prepared. Then we will meet after 15 minutes, 20 minutes.